In this video, we are going to discuss about series resonance. So here the RLC circuit, that is resistor, inductor and capacitor are in series. Okay, resistor, inductor and capacitor are in and the RLC series circuit when the circuit current are in phase with the applied voltage. Okay, so the current is flowing in this direction. This is your P. So the circuit is said to be a series resonance. So the resonance condition occurs in the series resonance circuit when XL is equal to XC. That is inductive reactance is equal to capacitive reactance. So we know that from this equation V is equal to I into Z, right? So what is Z? Z is equal to R plus JXL minus JXC. So if I substitute, I will get I into R plus JXL minus JXC. So at resonance, XL is equal to XL is equal to XC, right? So if I substitute here, I will get I into R because these two get cancelled out, right? So V is equal to IR. So a series resonance circuit is capable of drawing a heavy current and power from its main. So it is called as an acceptor circuit. Okay, so this is a circuit diagram of a series resonance RLC circuit. So at resonance, you can see the opposition to the flow of current is only resistors. Among the given impedance, only resistance circuit is present. So it will draw maximum current during that time. Okay. So these are the effects of the series resonance condition. The first is so at resonance condition, XL is equal to XC, so that the impedance value Z is equal to R. So you can see the impedance of the circuit get reduced. So impedance is minimum. Okay, so impedance is minimum and therefore the current is maximum for series resonance. So our next condition is the impedance of the circuit is minimum, therefore the current is maximum. So this is the first point and this is the second point. And third point is since the current is maximum, the power drawn by the circuit also maximized. Okay, because power is equal to I square R. Okay, this is equal to I square R. So at resonance condition, the current drawn by the circuit is very large. Therefore, the voltage drop across VL and VC also to be large. Okay. So, so at resonance condition, the excessive voltages build across the inductor and capacitor. So this circuit does act as a circuit breaker and reactors, etc., which may cause damages. So therefore, this series resonance condition must be avoided in the power system. So, however, it is used in the electronic devices such as antenna circuit of the radio and TV receiver and tuning circuit, etc. Okay, so this series resonance condition is used to increase the signal voltage and current at a desired frequency. So, so at resonance condition, series resonance condition, XL is equal to XC. So I can write omega L is equal to 1 divided by omega C, right? So omega square is equal to 1 divided by LC. So omega is equal to 1 divided by root of LC. So F is equal to 1 divided by 2 pi root of LC. So this F I can write it as resonance frequency. So at this condition, you can see if I plot the graph between F and I, so the current is maximum, right? The current is maximum at F is equal to FR. So this is my maximum current, I max. So what is half power frequency is this is I max, that is 3 dB value, right? I max divided by root 2. So this point is nothing but your F1, and this point is nothing but your F2. So I can write bandwidth is equal to F2 minus F1. So we know that I is equal to V divided by R plus JXL minus JXC, right? So I max is a frequency where you will get V divided by R, because at resonance frequency only you will get um, maximum value, right? So at F1, right? So at F1 I can write, so you can see at F1 I max values, I values I max by root 2. So I max by root 2 was equal to V divided by R minus R plus J omega L minus J by omega C. This I can write it as omega 1 L minus omega L C. So this I can write it as V divided by R into root 2, because I max value is V by R, right? So if I equate, I can write R plus J, instead of omega 1 I can write it as 2 pi F1 L minus J divided by 2 pi F1 C, that is equal to R root 2. Okay. So this entire term you have to, since it is in terms of since it is a magnitude value, so I can write it as V divided by R plus J XL minus XC, that is equal to V divided by R root 2, right? So V into root of R plus XL minus XC the whole square. Okay, that is equal to V divided by R root 2. So this is your I, and so if I take magnitude of this values, okay, if I take a magnitude of this value, and if I equate I is equal to I max at F1, I can write it as I max by root 2, right? That is equal to V divided by root of R plus XL minus XC the whole square, that is equal to V divided by R root. So if I square this term, I will get R plus XL minus XC whole square is equal to R square 2. Okay, so this I can write it as R square is equal to XL minus XC the whole square. So this I can write it as omega L minus 1 divided by omega C. Okay. So R is equal to So plus or minus R is equal to omega 1L minus 1 divided by omega 1C. In similar way, at F is equal to F2. At F is equal to F2, I can write this is nothing but I max by root 2, that is equal to V divided by root of R square plus XL minus XC the whole square, that is equal to V divided by R root. So if I square this term, I can write R square plus omega N by omega 2C, that is equal to V square by R square 2. So equating this two term, R2 square is equal to R square plus omega 2L minus omega 2C. So R square is equal to omega 2L minus 1 divided by omega 2C. So R plus R minus is equal to omega 2L minus omega 2C. So R is equal to omega 2L plus 1 divided by omega 2C, right? So if I multiply omega square on both side, omega 2 on both side, I will get 1 divided by C plus 1 divided by R omega 2, that is equal to omega square L. And I can write this one as omega square, okay. Whereas if I multiply, divide the whole term by L, I will get 1 divided by LC plus R omega square by L, that is equal to omega square. So I can write omega square minus R by L of omega 2 minus 1 divided by LC is equal to 0. So this I can write it as omega 2 is equal to minus B plus R minus B square minus 4AC divided by 2A. So what is B? B is nothing but R by L. Okay, and plus or minus B square. B square is R by L whole square minus 4 into L. A is 1 and C is minus LC divided by 2. So this I can write as R divided by 2L plus or minus 1 divided by 2 root of R by L whole square plus 4 divided by LC. So if I bring the 4 inside, 2 inside, it will become 4, right? So R divided by 2L plus or minus root of R by 2L the whole square plus 1 divided by LC. This is your omega 2. So similar way, if I take this equation, this first equation, so minus R is equal to omega 1N minus omega 1 divided by omega 1C. Okay. So I'm going to multiply omega 1 on both sides. Okay. Then I'm going to divide the whole term by N. So you will get omega 1 square is equal by 1 by LC plus R by L of omega 1 is equal to 0. Okay. So what is omega 1? Omega 1 is equal to minus B. B is R divided by L plus or minus B square. B square is R by L whole square minus 4 into minus LC divided by 2A. So minus R divided by 2L plus or minus by 2 root of R by L whole square plus 1 divided by 4 divided by LC. So this I can write it as R divided by 2L plus or minus 1 divided by 2. So if I bring the 2 inside, I will get R divided by 2L the whole square plus 1 divided by LC. So we know that the bandwidth, what is bandwidth? Bandwidth is equal to omega 2 minus omega n. So if I solve this one, I will get R divided by 2L minus of minus R divided by 2L. This is equal to R by L. So the bandwidth value is R by L. So we know that Q is equal to 2 pi into maximum energy stored by energy dissipated. So this I can write it as I into XL divided by I into R. Or otherwise I can write it as I into XC divided by R. So what is XL? XL is nothing but omega L by R, omega R, or 1 divided by omega RC by R. So this is your Q. Okay. So if I substitute omega R is nothing but 1 divided by root of LC, right? So if I substitute here, Q is equal to 1 divided by root of LC into L divided by R. So here you will get 1 divided by R into root of LC. So Q is nothing but your quality factor. Okay. And it also determines the selectivity of the. So if we see this curve, here the I is looking like this. Here for this one the R value is minimum. Okay. So if I choose the R value a little bit higher value, I will get the curve like this. Okay. So this is for R1. So here the R1 is greater than R. So if I choose R as greater than R, so you will see the curve, you will have a white band. So selectivity is reduced, right? So yeah, we know that the I is opposite to that of inverse of R. So if I plot the curve for R versus F, so you will get the minimal value. Okay, this is your FR. So and this is nothing but R minimum. Okay, so here you can see Q is equal to 1 divided by what is 1 divided by root of LC? 1 divided by root of LC is omega R, and R divided by L is nothing but your bandwidth. So I can write Q is equal to omega R divided by bandwidth. So this is nothing but omega R divided by omega 2 minus omega 1 So this I can also write it as F2 minus F1. Okay. So F divided by, I can write it as bandwidth also. And in this I also can write like this also you can write. Okay. So here I can write 2 power. Okay. So what is 2 power? 2 power is equal to I into R. Okay. What is apparent power? Apparent power is equal to I into VR. Sorry, I into VR. The voltage across the resistance. Apparent power is equal to total voltage. Okay, total voltage into that impedance. Okay, impedance value. So then what is reactive power? Reactive power is equal to I into VL minus I into VC. Okay. So this is your reactive power. So what is half power bandwidth? Half power frequency. Okay. So half power frequency is nothing but F1 and F2 is your half power frequency. Okay. So you will get 2 values for F1 and F2. So if you see this graph here at this frequency, that is that omega value which is less than FR. Okay, omega value is which is less than FR. That is, I can take omega is equal to 0. So if I take omega is equal to 0, I will get XL is equal to infinity. So XC is equal to infinity. So FC is equal to infinity means it is open circuited. So if it is open circuited, there is very less current. There is no current will flow. Very minimum current will flow through the circuit, right? So the current value is like this. So if omega is equal to infinity, the XC. So the XL value is nothing but infinity. Therefore, that is open circuited. Okay. So if it is open circuited also, the current value is minimum. That is when FR is that is omega is greater than FR. So only at F is equal to FR, you will get the maximum current flow. That's it.